Lesson 3 is on annuities. So far we studied compound interest, and then we rearranged the formula and we talked about present value. Those just relied on a one-time lump sum of money. An annuity is different. An annuity involves a sequence of payments that are made at equal intervals of time. So for example, let's say you're going to invest $100 at the end of each month for the next 10 years. That's an annuity. There are regular payments that are happening. It's not just a one-time thing. So the period is a time period between two consecutive payments. The term is just the time frame until the last payment is made. So if you're going to do this for 10 years, it would have a term of 10 years. An ordinary annuity, the payments are made at the end of each payment period. So at the end of each month or the end of each year. An annuity the payments are made at the start of each payment period. This one is more for things like monthly bills. So an annuity things like mortgages and car payments. Right now, though, we're just going to talk about ordinary annuities. So as example 1, find the amount of an annuity if $1,000 is deposited at the end of each year for 5 years at 8% compounded annually. So 8%, and we're going to take $1,000, but we're going to deposit it at the end of each year for 5 years. So this is different. We're going to take $1,000 at the end of year 1 and deposit that amount of money at the end of year 2, at the end of year 3, and then we need to figure out, because there is interest, so this amount is going to grow over those 5 years. How much would you end up with in the end? At the end of year 1, you're going to take this $1,000, and I'm just going to draw this. It's a time diagram. So a time diagram. If I come over to here, I'm going to use the compound interest formula. So remember, the compound interest formula is just the principal times 1 plus I to the n. And since this is compounded annually, I don't have to divide my I and multiply by my n, because it would just be dividing by 1 and multiplying by 1. So at the end of year 1, I'm going to take $1,000 and deposit it. I have 1 plus my interest rate is 0.08, and my exponent is going to be 4. Because I'm putting it in at the end of year 1, because it's an ordinary annuity, I'm going to still have 4 years left in this annuity. So what I end up with there is $1,360.49. At the end of year 2, so that is deposited, it's going to grow for that next 4 years. At the end of year 2, I'm going to make another deposit. So something else is going to happen now. I'm going to take that $1,000 and I'm going to invest it at 8%. Whoops. And the exponent would be 3, because there's still 3 years left in this annuity. The interest I would gain in those 3 years would be $1,000, or the final amount would be $1,259.71. Year 3, I'll just continue. I take my $1,000. It's going to grow at an interest rate of 8%, but I still have 2 years left for that $1,000 to grow. So in the end of that 2 years, I would have $1,166.40. 4 years, you kind of get the idea. I'd have my $1,000. I would deposit at 8%. There'd be 1 year left for that to gain some interest, so it's not that exciting. At the end, I would have $1,080. 5 years, I'm just going to have my $1,000. It doesn't really have any time, because at the end of 5 years, this would mature, so I would just be able to invest the $1,000. I'm not really going to gain any interest, because I'm just depositing it and then cashing out the annuity. So if I add up all of those values from each investment each year, I would have $5,866.60. So the final amount of the annuity is $5,866.60. Okay, so we are not going to want to make a diagram like that every single time. If your payments were made monthly for 10 years, that would be a lot of work to try and do that. So of course, I'm going to kind of abandon making these diagrams now because we do have a new formula to learn. So here is our ordinary annuity formula. We have a new variable here. Otherwise, a lot of things stay the same. We still have an I for the interest rate and an N for the number of compounding periods. But now we have an R, and the R is the amount of the regular payment. So when I see an R, I think of that as a payment. So if the payments were $100 a month, the R would be 100. One thing that we are going to be careful of, not every example has to be this way, but for us, the compounding period for our examples is going to be the same as the payment period. So that's going to make this a little bit easier for us for this lesson. So calculate the amount of the ordinary annuity of $100 if $100 is deposited at the end of each month for 30 years at 6% per annum per year compounded monthly. So you notice that it's being deposited at the end of every month and it's compounded monthly. So that's what I mean. That's going to, otherwise we would have to use a timeline and it would get a lot more complicated. So those two things are going to match for our examples. Calculate the amount. It's $100 that's being deposited at the end of each month for 30 years at 6% per year. So I definitely don't want to make a time diagram for this, but I'm going to have my R, A, I, N. So this time it's rain down the side. My regular payments, think of that R for regular payments, are $100. The A we don't know, the final amount that you'd end up with in the end, 6%, but the same thing goes here. It is monthly, so I'm going to have to divide by 12. Same as before for compound interest and present value. And then I have 30 years, 12 times each year. So I have 360 payments. Our formula looks kind of confusing at first. There are these square brackets, but it's just kind of to try and keep things separated. I am going to usually follow BEDMAS to do this, but scientific calculators can do a lot as far as typing things in with brackets and maybe not writing down as much as I do if you can figure out a way for your calculator to do this a little bit faster for you. So our regular payments are 100. 1 plus the I, which is the kind of thing we've seen before, to the exponent n, which is 360. And then we're going to minus 1 and divide by the interest rate, which is 0.005. So it's just a little bit more complicated, this formula. I usually use BEDMAS. So what I might do is type all of this into my calculator here. You're going to want to leave values in your calculator. I've seen a lot of you clear your calculator all the time. But if I had this, once I type all this in and I get this value on my calculator, don't erase it. Just multiply it by 100. Leave things in your calculator to make it easier for you. So when I type that in, 1 plus 0.005 equals, to the exponent 360 equals minus 1. I get, so you're just letting your calculator do a lot of this for you. And usually if I am going to write down numbers, I like to have a lot of decimal places. Sometimes I actually write down all the decimal places that I see, because the more accurate your answer, you'll see that it'll match the textbook solutions. And also it's money, so you want to get as accurate as you can. If you just rounded this off to 2 decimal places, you'll notice that your answer will probably be quite a bit different than mine. It's not that it's wrong, we just, it's not quite as accurate. So when I'm done, I'd multiply my 100 times the 5.02 number divided by 0.005. So that's a lot of money, right? But it's been a long time. It was 30 years, $100 every month. And people that are smart, they do this. They make regular investment payments They watch their money grow, and then at time for retirement, they end up with quite a bit of money, a lot more than they would have if they had have just put it under their mattress. So just as a little example here, you had 360 payments of $100, just to show you. There were 360 payments of $100. So that's $36,000. If you had to put that money under your mattress every month for 30 years, you would have ended up with just $36,000. Because of interest, we ended up with a lot more than that at the end of 30 years, because your money has been growing due to the interest it was accumulating. Example 3, so that you don't have to do this. This is just sort of kind of because I think that's interesting for you to see. Example 3, Andre would like to have $1 million for his retirement in 25 years. So this sounds more like a present value kind of thing. He wants to have $1 million later on. How much must he invest each month now at 6% compounded monthly to reach his goal? So he wants to invest each month, and notice it's going to be compounded monthly. Those have to match for us to use this formula. He wants $1 million, so that's actually the final amount. So instead of rearranging the formula like we did for present value, we're just going to sub in the A. So if I write RAIN down the side, the regular payment is what we don't know this time. So I don't know what the regular payment is, but I know the final amount is going to be $1 million. The I is going to be calculated the same way, 0.06 divided by 12, because it's monthly, so I get 0.005. And the N, this is for 25 years, every month, so we get 300 payments. So we know a lot of the information, but we don't know how much the regular payment is. So I'm going to use the same formula. This time I know the final amount, so I'm going to sub in for A, which is $1 million. I'm going to sub that in on the left-hand side. The R is what I don't know, so let's just leave that unknown for now. 1 plus 0.005 for my interest. 300 payments minus 1 divided by 0.005. So then it just comes down to, being able to use your calculator and work backwards to find the R. The very first thing I would do all of the time when I'm solving for R, if I multiply this side by 0.05, these would cancel. So I want to multiply this side by 0.05. And you might just see me go like this, because I want to multiply this side by 0.005. So when I do, I get 5,000, and then I don't have a fraction anymore on the right-hand side. I am also able to figure out what's inside the brackets here. So 1 plus 0.005 equals, to the exponent 300, equals minus 1, gives me 3.4649698. And you might be annoyed with how many decimal places I'm using, but I'm trying to make my answer as accurate as I can. Now what? We have to get the R alone. So do you see that we just have to divide both sides by 3.4649698 and divide that side. So divide this side as well. So this is kind of working backwards to find the R. 49698. So if I divide that side, I'm able to find out what my regular payments should be. And I get $1,443.01. So this is quite a large monthly payment, but Andre wants $1 million in 25 years. So if he just paid almost $1,500 a month, he would be able to save that much at 6% compounded monthly for 25 years.